the recording. All right, so let's carry on with this chapter here. So, stack overflows. The main thing we're going to do in this class is exploit buffer overflows. Later on, we'll exploit some other related things like format string vulnerabilities. So we ought to understand how it works and how you debug it with the GNU debugger and a few other things. So this is the most popular exploitation method. It was an underground secret known only by elite hackers in secret until 1996, when a person using the fake name Aleph1 published an article explaining it in terms people could understand. This created essentially this course in this whole field. I mean, this was a thing that showed us how this one technique worked, and almost all other techniques are minor variations of this one. This is the awesome way to take over a box. So a buffer is just an array. And in C, all right, so when you prepare a Debian machine, you've got to install Build Essential and GCC Multilib and GDB. Those are the tools you need. This Multilib enables you to run 32-bit code on 64-bit Linux. Now, if you're a Windows user, you've always able to run the previous generation of code because Windows is a commercial product intended to support old versions. Linux is not, but you can add it, and then you will be able to. So here's the first exploit. The fundamental problem is C and C++ were written a very long time ago. The original book, I think, was 1979, and they were almost equal to assembly language. Machine code. C is very close to machine code. It's very tied to the hardware. So it was written for people who would understand exactly how the hardware works, how bits work, how binary works, how things like exclusive OR and two's complement and bit flipping work and shift right and shift left. And those guys expected you to know all that. So they expected you, when you programmed C, to understand at the binary level exactly what it's doing. And the problem is, of course, decades passed, and modern generations of programmers have never understood the binary level of coding. They don't need to. They learn to code in Python and HTML and Java, and they expect the language to give them high-level constructs that work, like strings. And C does not do that. C gives you things that are very hardware-oriented. So here we go. We make an array. You define an array with 5 elements, and you give it 5 elements, and you can print the array, which is fine. The problem is, you can print the 5th element. The problem is you can cheerfully go off the end. In fact, 5 goes off the end. It's only numbered 0 through 4. So you can print array number 5. Now this shows you the problem. It is the programmer's responsibility to remember that there are only 5 elements numbered 0 through 4. But it executes this command. It simply takes the start of the array and moves forward 5 times the size of an element, going off the end, and then cheerfully prints the data it finds there. So now this is information disclosure. You're now seeing data that the programmer did not intend for you to see. And modern languages will not do this. Python won't. Nobody else will do this except C and assembler, of course. I mean, the problem is each individual instruction is just turned into an assembly language instruction. It never goes back to decide whether this instruction makes any sense in context. It just compiles it as if it's an independent statement. It is possible to make an array with 5 elements and fill them in. It is possible to start an array, go forward 5, and print the next one. And if you were a brilliant programmer, you might plan for this. You might want to use something in an unusual way, and it would never argue with you. Yes, sir, as long as I can do what you ask me to do, I will just do it. I would never question your wisdom. And the problem is that's unrealistic with modern programmers. So you can use GDB. You can see what's going on. We can do source code debugging here. Let me just set this up and get this going live. I should have a x86 machine available. There it is. Good. This is an emulated x86 machine on my Intel hardware, and I should be able to, it should respond fast enough for Linux. All right, it's still booting up, but it shouldn't take too long. It's slower. Yeah.
Excuse me. So C lends itself to this kind of problem.
Yep.
The buffer overflow.
C creates all these problems by being too close to assembler. Yeah.
Right. But if I'm a diligent C programmer, I would code all the potential buffer overflow.
Yes. This has been the argument for 30 years. The hardcore programmers have said, you just need to train the programmers better. They need to stop making these mistakes. This technique has failed. This is about as effective as telling teenagers, just quit having sex, then we won't have teenage pregnancy anymore. Tell people, quit smoking pot. You can try that. If they'd actually do that, it would be good, but you can't get that because programmers go to school, they learn from a book, they're at work, they're rushing to get things done.
Right,
Yeah.
but as a logical possibility, this potential problem of the buffer overflow could be completely eliminated even in C if.
Oh yes, and that was the idea. If the programmers are careful and they understand the problem, then they can avoid these problems. It has just turned out to be in practice that it's too difficult to get them all to remember it. And if you have a big, one programmer might be able to do it, but then your company grows and you hire new people and you have more people writing more and more code, and it isn't long before they start making these same mistakes. There's really about 10 mistakes they make, and they just keep making the same mistakes over and over and over for 30 years now. So that's why the pressure is on to switch to memory-safe languages like Rust. Python is safe. Rust is like C, almost as fast, and some people say it is as fast, but these problems do not occur in Rust. It's written to prevent these problems. And so that's a possibility. Anyway, let me see. Let me make a demo. All right, and go in there. All right, and
Rust
now.
is a memory-safe language.
Yes, yeah, and we'll do some projects later where you get to see. Rust does not have these problems. So let me put this one in there. Nano array.c. See if I can get it without making too many mistakes. And it's main. All right, come on. All right. A curly brace at the end, I think. Good, okay.
There was a cut and paste command even in that, no?
Oh, there is, yeah.
There is, right.
Yeah, problem is I got an image there. I mean, I probably have, so array sub 5 %d, that should do it. Array sub 5. There. If I haven't made too many egregious mistakes, that'll work. So I can do gcc minus o array and array.c. Okay. Hey, it's compiling without complaining. All right. However, array sub 5 is 0. Now let's change it a little, make it more fun. Let's print sleazy way. Let's try 3 bytes here, because it could be almost anything off the end there. I could make a loop, but this might be enough to make the point. All right, let's try that. Okay, they're all 0. Let's try CY. Now we'll use GDB. Let me make this higher on the screen and a little bit bigger. All right, we use GDB GNU Debugger in quiet mode because it prints an ugly message on the screen otherwise that irritates me. And we'll run the array. And, I know why. Let me do this. This is the first time I'm going to do it the easy way. I'm going to recompile it with symbols. If you do -G, it will add debugging symbols to the executable. And by the way, that will make it bigger. Let's take a look at that. Okay, right now it's 15.9K. That's how big it is. Now if I compile it with symbols, -G, now it's 17K, so it's gotten bigger. Now I can do GDB on that, okay? And now I can do source code debugging. If I type list, it will show me the C source code. And so I can say, let's put a break before line 6. All right, now I'm going to run it. It's going to stop before at this point, so now the array is initialized. Now I can print array. It will show me it's 1, 2, 4. Now I can also print, I think it's pointer array. Yeah, that's the address where it's stored, FFFF3E70. Now I can do info registers. The registers are the things
what is stored at that address?
This array.
The full, yes.
Yep, that's where it starts, yep, at 370. And I can do info registers and see all the registers, and this is 64-bit code, so the stack starts here at 370, and the stack frame ends at 390, RSP and RBP, and the array is here at 370. So it's right at the start of the stack. So I can now examine the stack bytes. Let's do 16x RSP. All right, so here's the bytes on the array, and you see it right there, 0, 1, 2, 3, 4. That's the array. And the next few bytes are all zeros. That's why when I printed it out, I got zeros here. But if I went, this is 5, 6, 7, 8, 9, 10. If I go around 10 or 11, I'll start seeing interesting results. And, all right. Yeah.
What's the 16x? What's the
This means examine 16 words in hexadecimal starting at this point. That's what it is. This is
hexadecimal. You don't use the H.
I chose hexadecimal. Now I could do like characters, and then it would interpret them as printable letters, which they aren't. That's why I usually use hex. That's X. That's individual bytes. And here's that's interesting. Somehow I got it. Maybe it's W to get back there. Yeah. Yep. W got back to it. X changed this back to hex, but it didn't change it back to 32-bit groups. W got it back to 32-bit groups. Anyway, we'll do this. We'll use this program a lot. GDB is a full-featured debugger, and it's got all the power you could ever want, but we're only going to need like 10 commands. That's all we're going to need in this class. A few simple ones are all you need to do buffer overflows, which is mainly what we're doing. So now, we got a buffer over, yeah, go ahead.
Sam, forgive me.
Yeah.
I think this is a question that you dealt with
No, that's fine.
last week in chapter 1. Can I, let's consider for a second the stack of functions. You know,
Yeah.
all the functions are called, there are on top of each other. Can I assume that each call can I assume that all the calls occupy contiguous segment in the memory?
Yes.
Yeah.
Yes, in fact, it's a very good question. In fact, let's look at this. Let's look at the assembly code. We'll get into this more later, but let's, well, actually, this program is not a good one, but we'll make one later. Where you see a function call, at the start of every function call, it creates a new stack frame for that function, and it always takes the next available data on the stack. So they're filed up like trays. And we can't see it very clearly on this because I didn't make a subroutine, but we'll have others coming up that have it. So this is good. All right, so we use GDB, we can see it, you can see the stack, all right. And so here's a few commands: list, runs the program, break, and X. Those are the commands we used right now. That's enough to let you see what's going on the stack. All right, so now we'll make another one with denial of service. Here I print 10,000. If I print 10,000 off the end, with the address and the value, then what will happen is it will get up to a certain amount and then crash. So this is a kind of denial of service. Now you notice, let's make this one. This one is worth making. Let me just fit my two things on the screen at once. Let's get out of the debugger and copy the existing one. Array2.c, then nano that one. All right. So int I array 5. All right, and now you're just going to make a loop. So for I equals 0, I less than 10,000, I plus plus, and then printf. Just going to do %x, two hexadecimal values. All right, I'm going to do the pointer array sub I to show the address where it is, and then the value that's stored there. There. And that should do it.
Should you eliminate the space in between ampersand and array?
I probably should get rid of it. I don't think it matters, but it might. You're right. There. That's good. All right, so there it is. And let's try this one. So I'll compile it, array2, and make the output array2, and I'll compile it with symbols so I can easily debug it. And there we go. Oh, I forgot to declare I. Right. You have to declare variables before you can use them. And so I, there. All right. So there we go. All right. And if I run it, it ends at 221 DDFFC, and then it crashes. And if you want to know why, we can debug it. And then we can list, and let's just put a breakpoint for line 6. So it's before it starts printing things. I'll run it to that point. Now the program is going, and now I can see the memory segments with info proc mapping. And this shows me the memory segments that are used by this program. And I can try to make them fit on the screen as best I can. Let me make this bigger, just to make life easier. All right, now let's try it again. Info proc mappings. Okay, now remember when it crashed, it went up to 221 DDFFC. 221. Well, I thought I'd be able to see it here, but I'm not seeing that memory segment, 221 DDFFC. I thought I would see it. Oh, there's an important reason why I wouldn't, because this box probably has address space layout randomization turned on. So let me fix that. See, in fact, I can tell by just running it twice. Let's quit. Okay, so let's run that program and let it crash. Yep, now it's 3.6. Next time it's 3.5. It's address space layout randomization. Every time you run it, it randomly relocates in memory. Now that's a good security measure, but I don't want it, so I'm going to get rid of it. And this is going to come up in the projects, and I'll just get the code from one of these projects here. It'll probably be in this one.
I think
Yep, there it is. Disabling ASLR. Those are the 3 commands you need. Yeah. And you have to kind of do it this way because you have to be root a little bit longer than you might expect. So sudo shu minus basically changes you to root, and you stay that way. Now and I put in my password. Okay, now I'm root. Now I can do this. This is what turns off randomized VA space, which is a kernel parameter for the operating system. And now I can exit. All right, now, if I just run this program, it's FFFEFFC, and it's always the same. So now I can see it quits at this point, FFFEFFC, and now if I GDB it, and I think I have to run it. I don't think I can do this now. Right, so I have to run it and have a breakpoint. So I'll break at 6 and run, and now I can do info proc mappings. Okay, and now I'm looking for FFFFEFF. And still not finding it. Well, all right, I don't know what's going on there. But I actually, in this case, I think I ran off the end of the entire address space. FFFFEFFC. Apparently, FFFF0000 is the end of something. And I don't know why the stack, where is the stack? There's the stack. So it's actually a little screwy. It should have been 7 FFFF0000. And this printed, it looks like this didn't print the whole address. It only printed the lower part of the address. Oh, I think I only printed the lower 32 bits. I think I need to have %X. Now we're getting a little bit ahead of things, but that's fine. C format strings. %X, I think, is only for 32 bits. I think I need to use %P for a 64-bit pointer. See if the AI can figure it out. Yep. X is printed in hex. P is used to print the memory address.
So then, no, you have to combine an XP, so
X and P.
and percentage.
Yeah, X is for regular integer values, which are only 32 bits long. P is for hexadecimal. I think if I change it to %P, we'll get the right answer. So let's edit that code. There we are. And print %P. There. Compile it again. And run it again. Yep. And now you can see it's 7 FFFF F100 is what it couldn't get to, and that's what we saw when we looked at the memory map. Back up here, the memory map showed, well, I'll just do it again because that's like something like 10,000 lines up there. Minus Q, array 2, list, break, line 6, and run. So I get the program running and the stack is set up and stuff. And now I can do info proc mappings. And you can see the stack goes to this address, 7 and a lot of F's with 3 zeros. And it couldn't, that's what it did. It's trying to go there, and it goes up by another 4. It'd be at that address off the end. So that's why it crashed. I hit the end of this memory segment, and I tried to read beyond it, and it won't let me. So I hit the end of the memory that was allocated for this process. Good, let me check for questions up here. All right. Good, okay. Anyway, so.
Forgive me, sir.
Yeah.
Why would we want the address space layout randomization be on?
Oh, it makes you safer because, as we're going to find out, when you do this buffer overflow exploit, you inject some data in, and then you interpret it as code and run it. So you're going to try to jump to an address of the stuff you injected. And if you have address space layout randomization turned on, you can't find it. You don't know where it is.
Right, so I don't want that to turned on, right?
Well, when it's turned on, it makes you safer. A whole generation of attacks don't work. Yeah, so it's on by default. We turn it off to make it easier to exploit the box. And eventually we'll learn how to defeat this, but it's difficult.
Okay, so it is on as a safety for the user,
yes.
But is off as an advantage for the hacker.
Yeah, of course. And as we're the attacker, we're going to have to learn how to overcome these defenses. But we start with the easy case, where that defense is not there, and then later on we'll learn how to defeat it. All right, so there we are, reading past the end, and there you are, address space, yes, good, it's all here. So we've done this. ASLR shows it changes every time you turn it off. Oh, good. All right, so you debug it, get the memory map, and you can see everything's fine. All right, so the stack. We just ran off the end of the stack. The stack is last in, first out. Now, in 32-bit code, which is what we'll use at first, ESP points to the top of the stack, and you push to put things on the stack. And EBP pop takes things off the stack. Pop EAX takes the 32-bit word at the top of the stack, puts it in EAX, and then shrinks the stack by 4 bytes. All right, EBP is typically also called the frame pointer. This is the bottom of the current stack frame. Yeah, we'll use this a lot. All right, and so local variables, you refer EBP plus 10H. Local variables stored on the stack are calculated from EBP or ESP in assembly code, because you have, when you jump into a subroutine, it creates a stack frame to store local variables, starting at EBP and going up to ESP. That's the bottom and top of the stack.
Yes.
And so all your local variables have addresses like this: EBP plus 10, EBP plus 20, that sort of thing.
So the result is the ESP.
Well, so EBP plus, you could do ESP minus something, or EBP plus something, yeah. And then, yeah. Go ahead.
Forgive me, just one thing that I didn't get it.
Yeah.
What are we recording into the register? The address or the value?
If you put square brackets around it, then it's the value.
So
you take this is an address, and you add a fixed amount to it. Now you found the address of one of the variables on the stack. You find the value there, and you put it in EAX.
So the square brackets may be the value.
Yeah, square brackets mean dereference.
Dereference.
Yeah, good, very good.
Thank you.
Sure, all right. So, all right. So functions in the stack, right where we're going. So when you call a function, it needs to, the calling routine needs to stop processing and save its current state, transfer controls to the function needs to do its work and then exit, then it needs to restore the state of the calling function and resume. All these things have to happen. It's the same thing as if you're, reading a book or something, and then the phone rings. You have to put a marker in the book, shut it, go answer the phone, then come back and pick up where you left off. The problem is this process is not very strong, not very secure by default, and we're going to exploit it. So here, after you call a function, it will save the return value and the previous EBP for the previous stack frame, and then have a new stack frame up here. But so if you're able to fill this array and go beyond the end of it, like we just did, you could modify these values. If I can write to this array, I can write past the end of this array and change these values. And what I'm going for is the return pointer. Now when I return, it will go to the address of my choice instead of the address the developer wanted. That's how you take over the box. But you have to understand what address to put in to go to the code you want to execute, and that's why ASLR helps. Because then it's random, so it's hard for me to figure out what address to put in there.
So basically, I inject the whole code.
Yeah, you inject it.
But then I don't know the return part of my code where it is located.
Well,
So
yes, you have to find it. And we'll learn how to find it.
Part of
What you do is you put in a non-repeating pattern of letters, and you can tell from what return pointer turns into what part of those letters controlled it. If you're right on target.
Sorry, forgive me,
Yeah.
I'm still confused about
That's
this.
fine. Yeah.
Because here in the previous, you had said that the square brackets make it a memory address, so I'm passing
Oh,
the
yeah,
memory
square.
address.
Yeah, it's the value at that memory address. That's what it is.
So I'm passing.
Yeah, exactly
So
right.
I'm recording the value.
Yeah, that's the value. Yep, square brackets mean you dereference that memory address and find the value.
Without brackets, then I'm recording the address.
It could be an address or a value. Could be anything. It's a general purpose register. Yeah. Good. Very good. All right. So this is the point of the stack. This is why we have this strange last in, first out thing for just this reason, so we can have functions, and functions can call a sub-function, and a sub-function, you have a dream within a dream. You know, many layers down, you can have, often your stack is 10 or 20 frames deep, because you start with main, you call, take input from the user, that calls, do a calculation, that calls print or something, many layers down. So, the prologue is the start of a function, which creates the stack frame, and so it copies ESP into EBP. First it pushes EBP onto the stack, then it puts the top of the stack into EBP, so you start a new frame at the top of the previous one, and then you shrink ESP by enough room to make room for all your local variables. That's how it works. And we'll see that. So you end up with something like this. You have an array up here. So here's a function, and I think we're going to do this one. So let me create this one. I could have had these made in advance, but it's not too hard to make them now. All right. And all right. So I'm going to get out of here and nano function demo.c. All right. Right. That should do it. All right, let's see if I followed that up or not. That's called fndemo.c, so gcc minus g minus o fndemo.c. Okay, cannot find fn, oh, I got a p instead of an o in my command line here. O is for output. I don't know what p is. All right, there we are. All right, now, return type defaults to int, that's fine, that's just a warning. I didn't bother to tell it the main function was an integer, so I should be able to run that. And I can. Okay, so all it does is it calls this subroutine that doesn't do anything, and then returns and then prints that message. But the point is we can examine it in GDB now. And we can watch it go. So GDB fn demo. All right, so we list, and there we are. So I would like to first put a breakpoint at line 10. So I break inside main, and then I'd like to also break inside the function, so I'll put another break at line 5. All right, so now if I run and get to this point, I'm about to enter the function. So now if I do info proc Okay. If I do info registers, you'll see I made a mistake here. These are 64-bit registers, which is fine, but I wanted to make life easier and start with 32. So let's do it with 32. All I do is I recompile it here, and I put a minus M32 here. I'll make 32-bit code instead of 64-bit code. It'll run just the same, but it'll be a little bit simpler in GDB. All right, so now I run it here. I list the C code is exactly the same, of course. I want a break at 10 and a break at 5. Now I run to 10, and now I do info registers. All right, now I get the 32-bit registers, a little bit simpler to deal with. And the ones I care about are stack pointer and base pointer. So the stack goes from C0 to C8, not very big at all. So I can examine, say, 8x ESP. All right, from C0, which means 0, 1, 2, 3, the bytes here, they're in that order because this is the most significant byte on the left of these 32. That's something you get used to. The actual byte C0 is here. Then this is the byte called C0. And that is here, it's E0. Then this is C0, 1, 2, and 3. This is C4, 5, 6, and 7. That takes a little getting used to, but it is logical because these are like 32-bit integers. So the most significant byte is on the left. But that's little endian. That's how it works. The little number goes first. So it has this weird result. So anyway, there's 4 words. This one starts at C0, this one at C4, C8, and CC. This last one is CC, CD, CE, and CF.
Because you're counting the addresses.
Yeah, those are the addresses. All right, so there you see the stack. I'm inside this main routine, and the stack only goes from C0 to C8. So this is the stack, those 2 bytes. That's it. Okay. Now if I continue, I'll go into the subroutine. Now I'm inside the function. Now if I look, remember the ESP and EBP were C0 and C8. But if I look at them now, it's 90 and B0. So it made a new stack frame above the previous one. So if I do X, say, 16X ESP, okay, C0 to C8, here's the stack frame of the calling function. But the called function had a stack frame that goes from 90 to B0, so that's what it has. This is the frame, stack frame of the subroutine. Yep. And that's because I defined an array of 5 in here, so it needed some room. So here's the subroutine. So you have the stack frame of the calling function, and it ends with the EBP of the one above it, which was C8. This is the stored EBP from the calling routine. Remember, the calling routine stack goes from C0 to C4. And anyways, I'm not quite sure what C8, but this is EBP. Here's the most important thing, though. That's the return pointer. That's where it picks up where it left off. And you can tell, you can disassemble main. All right, so here's the main. Here it is calling the function. So the next word is 56, 55, 61, C3. That's where it wants to resume when it comes back. And that's what you see right there. That is the return pointer. So if I can write to that byte, I can take over the box. And that's the fundamental flaw we're going to exploit. Yeah. Yeah.
In terms of how the information is allocated into the different registers, I didn't get how this little versus big endianness works. So little endianness should start recording the hexadecimal code from the least significant byte.
Yeah, so it means
the least significant byte is at the highest address and then go down on the stack.
No, it's at the lowest address. That's right. The little one goes first. So this is 90, 91, 92, 93.
Little goes 91, 92, 93.
Yeah. Yeah, and so this is the least significant, and that's the most significant. That's why they call it little endian. And so it has this effect. If you write a 4-byte integer, 32 bits, the most significant byte is the 4th one, not the first one. So that means it creates this weird situation where the actual addresses go backwards.
But that is something that happens behind the door, behind the curtains, under the hood. I never see this little endianness recording.
Well, you do. For example, up here, we had a literal 1 and 2, and there they are. And that's what a 1 looks like. If it was big endian, a 1 would look like 0, 1, 0, 0, 0, 0, 0, 0.
Even here?
If it was big endian, yeah.
Okay, that is
Yeah. Well, it might rearrange it the other way here. But anyway, in actual memory, it might be easier to see if you do this, if I show it 1 byte at a time. So if I print them as, say, I think B is bytes. Yeah. Now you see them in order. And so let's do more of them, like 64. Now we can find 0002 there. This is how a 2 is stored. 2000, little endian. And now the bytes are in the expected order. 8, 9, 10, 11, 12, 13, 14, 15. If you print the bytes 1 at a time, they're in the right order. But if you print the 32-bit words, it reverses them so the word is correct. So it shows the correct integer value. This is very good. You're right on target to try to keep this straight. It takes a little getting used to, but you're going to see it a lot, so we'll have plenty of time to get used to it. All right, so...
but we should play safe in this case, because we should be dealing with little endian for the work we are doing.
Yes, yeah.
As
far as I know, there are no big endian processors. I don't even think ARM is. So little endian is what we're going to use, I think. Yeah. All right. So now we got a function, and all right, return to the function, you debug and set breakpoints, and so on. We've done this essentially. Yep. You see in main, you see the stack frame, you see your function. All right. And so we've done all this. All right. So now, now we'll talk about the preamble. This is another good thing to know. So let's go back to here. So here's the main function. So it goes down here, it does various things, and here it calls our thing called function. An address. Okay, when you call a function, let's see what it does. Let's disassemble function. Okay, here's what function does. This is the preamble. These 3 commands. This is what creates the stack frame. It pushes the old base pointer onto the stack. Then it moves the current base pointer into the ESP and then subtracts 20 from it. So this is, I think this is moving this into there. This is Intel frame. It's moving ESP. Yeah, it's moving ESP to EBP. This is source destination, because the destination can't be a constant. So it moves ESP into EBP. So it saves the old EBP. It takes the first available byte, and that's the new EVP. That's ESP. And then it subtracts 20 from it. That's making room for the local variables. These 3 are called the preamble, and they create the stack frame. So before you do any actual processing in your subroutine, you prepare the stack frame, so you've got some memory to work with. Then you do whatever you're supposed to do down here, which in this case is just add something. And then when you're done, you do leave and return. And the leave pops the EBP off the stack and into EBP for you, and the return pops the next value and puts it in EIP. And that resumes. So this is what pulls those 2 values at the end of the frame, the EBP you put there and the return pointer that the calling function put there before it came here. That's how it works. And so you get used to this. There's a preamble that prepares the stack frame, and there's a epilogue that cleans up. And what we're going to find, of course, is this will fail if the data has been tampered with. And the return, instead of returning to the calling function, will return somewhere else chosen by the attacker.
The prologue kicks in once we start an executable, right?
Once you call a function. And when you call an executable, you start in your Linux and you run main, and it does something similar, although it's a little more complicated.
Okay.
That's why we're going to exploit subroutines. This is a mistake that held me back for years. I kept trying to exploit main, and the calling stack structure of main is complicated. That's why you make a subroutine. Once you have made your code, when C is just calling next layer down, it's easier. But we'll see, and especially when you get to ARM, we're going to have to do it the other way. All right, so that's what goes on here. We disassembled the function. This is the prologue, like you say. You save the EBP, you move the ESP into the EBP, and then you subtract something to make room for local variables. All right. So saved return address is on the stack. We've been here. That's the address of where you're going to. All right. So now we can talk about the stack buffer overflow exploit, which is pretty simple. So here's one with a stack with a buffer overflow vulnerability. And I think I'll just, again, make this here. We've got plenty of time. But it is time to take a break. It's about 7. Let me stop this recording. Let's break this into chunks.